right, yeah, thank you very much for the invitation to give this talk. I think we're sort of out of time for my talk. We're at the end. I will try to be fast, but what I would like to do in this talk is to add a new modality to the zoo of multimodal foundation models and really expand the scope of foundation models. Tabular data. Why? Yes, I'm sharing my screen. Let's go away. Okay. Why should we care about tabular data? Or what is tabular data in the first place? So one example here, it's really this good old-fashioned tabular data that probably most of you, when you took Machine Learning 101, you fit a random forest or something to this type of data. There is a data that is organized in rows, and there's features and columns, and then there's a special feature that you want to predict. You have training data, and then there's test data where, in this case here, for a new patient, you want to predict whether they have early stage Alzheimer. You can wait 3 years and you know whether they have early stage Alzheimer, but then it's too late. You want to predict this right now, and you have historic data. So that's a tabular prediction problem. The sort of personalized health models are a long-standing challenge. And if you can just take some blood of a patient and then say, hey, they have early stage Alzheimer's, this is really going to be helpful. And there is a lot of startups collecting data for billions of dollars, and it all comes down to tabular data in the end. Tabular data doesn't only happen in medicine, healthcare, but also finance, business analytics, insurance, and many, many others, like literally thousands of applications. Very related are time series forecasting tasks, where you have a signal over time, and then at this point you want to predict what's happening in the future, and you can predict energy prices, supply and demand, temperature, climate, etc., etc. Models for this. Maybe first, what is the current state of this field? It's sort of this last unconquered castle. People still use gradient boosting. People still use non-deep learning methods and not foundation models. It's still the case that for each data set, people run a single algorithm, and it's expensive training, and it leads to siloed models. Foundation models, of course, in contrast, take more data, but then fit one foundation model that can be used off the shelf without retraining, and that you can also, if you have many different problems from a particular domain, you can fine tune to that particular domain, and it just gets better, and there's information sharing across data sets. With Prior Labs, we do focus on this. While foundation models have transformed text and images, we hope to transform tables, time series, and databases. And we as a community are already on our way to revolutionize tabular data with foundation models. So one milestone was this TabPFN v2 publication we had in Nature. That's more accurate than previous machine learning in like 96% of the use cases where TabPFN applies. And it's also in particular more data efficient. So with 50% of the data, we can make predictions that are as good as 100% of the data with the next best method. So if you only have to screen like half the patients in order to get the same success rate, then that's actually a lot of savings for the health system. And well, we're in this open source session. Of course, we have released this as open source. There's more than 1 million downloads, 4,000 stars on GitHub for the software we released this January. All right, so what I want to talk about is TabPFN. Actually, we had a paper in 2023. This was sort of the small scale version, and then the V2 version that solved a lot of problems from the previous version, but sort of conceptually, it's the same thing. It's just solving some issues. So that's why I talk about them in one after the other, and then briefly show that this model out of the box also works for time series, and then talk a little bit about explainability and fairness, which are of course trustworthiness dimensions that are very important. All right, so TabPFN is a learned algorithm for small tabular data. It's in a sense a GPT-like transformer for tabular classification. You can frame this as next word prediction. You have the X, the Y, and then the xn plus 1, and question mark. Of course, you want the next prediction. It's not quite as easy. It's not a sequence, but you can see it like this. But to be more precise, you have a set of data, and you also want the probabilities. And in a nutshell, a PFN is just a neural network that takes all this data in context and then spits out this probability distribution. It has parameters theta, and these parameters are optimized by minimizing the average cross-entropy loss across data sets. Which data sets? Well, that's a big problem in tabular data. We don't have trillions of tokens. We have like thousands of data sets. And a data set will be basically a data point for us. So there is this huge dearth of data, and that's why we actually created all of our data that we trained on synthetically. We did not train on a single real data set. This is purely synthetically generated. And we train this in very standard fashion, like standard SGD. So pictorially, how does TabPFN train? So you have a data set that has this X train, that's and Y train. So Y train we want to predict. This is historic data, X test is a new data, and then the Y test, you take the Y test out and feed with a question mark, feed it here into a TabPFN that makes predictions. And then you just look at how likely is this Y test under these predictions, get your cross entropy, backprop that, and then iterate with a new data set. So every backprop step will have a new data set, and we synthetically generate these data sets. And then at test time, when we have a real data set, this X train, Y train, X test, for example, this medical example that I showed in the beginning, we can feed this into TabPFN and it makes predictions. So really, SGD just takes care of this for us if we have data sets that are representative of the real world data sets. So the only missing piece is this method to generate these synthetic data sets. We also have theory about what happens under the hood. So what happens under the hood is actually these synthetic data sets define a prior distribution. And what PFNs do is to actually approximate the base and posterior under this prior. So if our prior distribution is only linear regression data sets, then our TabPFN will be a linear Bayesian linear regression classifier. But we just put a lot more stuff in than linear regression. In particular, we put in structural causal models, and then we actually approximate the Bayesian posterior over these structural causal models. So I just mentioned structural causal models. So we integrate these principles from causality. We basically think, what might real world data look like? There's probably some causal relationships between some of the features. And so what we do first, we sample and initialize a causal graph. Then we sample connections between them. We sample where should the features be here and where would the Y be. The Y doesn't have to be a child. It can also be that Y is a cause of an X, or there's a common cause, a latent cause. There's all kinds of possibilities of structural causal models that could explain the data. And each time we sample a new structural causal model, we sample weights in here, activation functions, etc. And then there's two special inputs. These are epsilon inputs. They're therefore noise variables that we can instantiate in order to actually sample data from the structural causal model. So by instantiating these differently and forward propping them through this, actually what turns out to be a computational graph in PyTorch, we just get the instantiations of this is supposed to be x1, so that's x1, this is supposed to be x2, so this here is x2, this is supposed to be y, so this is y, and we sampled the data point. And then we can do this again and again. So here we sampled a data set with 3 data points. And then, well, in practice, we sample many data points with thousands of points. And if we do classification, then we also threshold it. All right. We also, in this prior, we have a simplicity principle that says we put more likelihood, more probability on simpler explanations. So we have simpler graphs are more likely than more complex graphs. We can have these complex graphs with all kinds of latent structure in there, but in order not to overfit, we actually favor simpler explanations, and that's why the simpler graphs are more prominent in our prior. And then here we just visualize some data sets. And on the left here, there's synthetic data sets, one feature against the other plotted. And on the right, there's real data sets. And to the naked eye, they sort of look similar. And basically, if we then call some of these points the training data points and other statistic data points, and we learn to solve classification, regression, etc., in these synthetic data sets, well, then there's really no reason that we shouldn't also be able to do it here. So we learn an algorithm that can do tabular classification or regression. The qualitative result is that we get very smooth and well-calibrated predictions. So here we have some toy data from scikit-learn, this half-moon data set, and what all the different types of classifiers predict. For example, decision trees are just very axis aligned, and TabPFN just makes very good predictions, and they're very smooth and well calibrated because, well, we train it with cross entropy loss. If it was wrong but certain, that would be penalized very heavily, and so it will try not to be wrong and certain at the same time, but rather calibrated. Right. Simplicity is, of course, well, it's a foundation model. I pushed this field of AutoML for many years. I still really like AutoML, but we built AutoML systems like AutoSQL that, like wrapped around scikit-learn, did some meta learning, built ensembles and whatnot. Super complex, takes like over the weekend, and TabPFN takes like 5 seconds in a forward pass and is better than AutoSQL. So that was the result we already had in 2022, where AutoSQL was here the leading method before. Like in an hour, got very good predictions, but TabPFN, like in a second, got better predictions. However, this was very limited in 2022. In particular, up to 1,000 data points, only 100 features, 10 classes, and only classification, not regression, not yet made for categorical features, missing values, uninformative features. So all the stuff you need in data science. So this wasn't usable, and that's why we built TabPFN v2, where we solved all these issues to a certain degree. Well, we not all these issues. We scaled up to 10,000 data points, which covers a lot in pretty much all the medical use cases. But if you have financial data with billions of data points, well, it's not going to cover that yet. And so there's still work to be done in order to also outperform classic methods in that regime. But now it can be used for data science. It can do categorical features, missing values, uninformative features. It just handles it all natively. And the results are sort of similar as before. It just performs a lot better than other methods. How did we get there? So we changed the architecture a bit. I'll show that and improve the prior. The new architecture actually really takes into account that there are rows and columns. So this is axial attention, first an attention over the features, then attention over the data points, and then iterate that 12 times. And in terms of results, so that this is from the Nature paper here now. So compared to things like linear regression, there's k-nearest neighbors somewhere down here. MLPs, SVMs, random forests, and then 3 different boosting methods that are sort of similar and all state-of-the-art, LightGBM, CatBoost, and XGBoost. It just, TabPFN is just a different category. This is on average across data sets. There are data sets where it performs worse. Here's one out of the 29 where CatBoost is better. But on average, it's clearly better. And also for regression, a similar trend holds, so the results are not quite as good there. We also haven't spent as much time on regression to be fair. We also compared 2 AutoML methods, and here AutoML is, of course, going to have its comeback. I can't leave the talk for saying AutoML is done. We integrated methods from AutoGluon, in particular post-hoc assembling, and that do push the performance of TabPFN actually from here to the green line, which in classification just makes this even that much better. But for regression, actually, you really need it in order to get better than AutoGluon. Here, the default is actually not better than AutoGluon, which is purple. But with the post-hoc assembling, you are clearly better than AutoGluon. And so it's an ensemble that's only of different TabPFNs is better than an ensemble of all the other methods. All right. What was this, me? Or Nick Erickson was there. He's like, oh no. No, Nick knows it very much. He likes this. Yeah, so some ablation. So TabPFN v1 was very bad for uninformative features because uninformative features really hurt neural nets. You see the MLP performance really tanking here when you just add some uninformative features. And well, in TabPFN v2, we just put that into the prior that there might be uninformative features, and then it doesn't care so much anymore. Same thing for missing values. We tell it in the prior that we punch a bunch of holes, and it shouldn't care about that, and it learns to deal with that. And yeah, categorical features it also can do. This is the number I quoted before. With 50% of the data, it's as good as 100% of the data in CatBoost. As a foundation model, we can fine-tune it. So we can fine-tune it to, in the Nature paper, we had these toy sign functions. So in yellow here, we have some data, but the TabPFN doesn't know that this comes from a sign function. So we only get the data points, not the line. And then you clearly see that it does make mistakes. It's not a great prediction. It's okay. But when you fine tune a little bit, just on some sine waves, it figures out, okay, sine waves are much more likely, and it predicts much better. And this translates also to the non-toy setting. So we now also did fine tuning on a broad collection of real data sets. You could think of this as sort of continued pre-training. It's sort of a weird data set mixture where we only train on synthetic and then we only train on real. Of course, we should mix this, and probably it's going to get better. But what this helps, what this gets is to reduce basically the remaining error from here to there by half. So really, like, also adding some real data does help and does make it better. Not surprisingly, of course, from a foundation model perspective. All right. Yeah. How can this be used for time series? Very easily. We basically just take the time series, take the time step. This is all univariate time series, which is sort of which has been the default in the time series community for a long time with Chronos, etc. So we take the time step, featureize the time step, basically just saying running index and the year of the date and the day of the week and the day of the month and the time of the day, etc. And we can do that, of course, for any time step, also in the future. And the y value is just the height of the time series. And then we xtrain, ytrain, xtest, and feed it into TabPFN. And that simple extension early this year actually achieved state-of-the-art on GIFTeval with the same model that was from the Nature paper, trained on synthetic tabular data sets. It never saw a time series before. It never saw this encoding before, and it never saw real data before. And it still was better than Amazon's Chronos and Google's TimesFM, also a much smaller model. And yeah, they trained on synthetic and real time series. And yeah, we were very surprised by this. We did not plan for this. We just evaluated it, and it worked. But this just goes to show that there's a lot to be gained in time series foundation models. And indeed, in the last 3 months, there have been 3 new models, Toto by Datadog, Yinglong by Alibaba, and Tyrex by our new partner in the consortium of ELLIOT and NXAI. And they, of course, train on real data, and we'll also now looking at fine-tuning and training on real time series data, because yeah, there's, I think, still a lot to be gained. All right, last point is explainability and fairness. So this is, of course, super important, especially in tabular data. There's a lot of reservations. People have worked with this tabular data for like 30 years with gradient-based methods and gradient boosting methods, etc., tree-based methods, and they like these. They feel that they're interpretable. When you have a boosting with 1,000 different trees, I feel it's very uninterpretable. But quantifying that, it actually makes these very, very jiggity predictions. The response surface is not very smooth and not very well calibrated. And that's why SHAP is actually not very interpretable for it. Whereas for linear regression, it's super interpretable, but the results are poor. And for TabPFN, it's similarly interpretable as for linear regression, but the results are better than both of the other ones. And then we also have some unique things we can do with PFNs for fairness and also for causal interpretability, which is the next slide. So we can actually in the setting work on counterfactual fairness. So counterfactual reasoning is basically this: what would the result be if this protected feature here changed? If like this data point, if this was not a man but a woman, what would have changed in their salary, or whether they get a credit, etc. So we do want to be fair, and there's all kinds of different definitions of fairness, but the one that actually gets closest to the letter of the law is this type of counterfactual fairness. But it's a really complex setting because you can't just leave out this protected feature, because there's a whole lot of features that are correlated with this feature, like size of, in medicine, for example, the size of the person, etc. Yes, so what you really need to do is you basically need to take out the interactions of this protected value in your relationships to the different features. So if you have a structural causal model, which we do for our pre-training data, we can just say this protected attribute here, we're going to drop these edges here and look at and resample the data based on the same structural causal model, but without these outgoing edges from the protected attributes. So we generate data twice. We generate the biased data, and then we generate the fair data. And then we learn to basically map the biased training data, the biased Y, the biased test X, to the unbiased Y. And this is just what we pre-train on. Again, millions and millions of data sets that we construct. And then we just learn to, in a forward pass, actually get the Bayesian posterior over structural causal models where the protected attributes, outgoing edges, are cut. And yeah, this of course then substantially outperforms standard methods, and I'm very excited about this. A similar work we did with Bernhard on interventional predictions with DoPFN, which is on Archive. So there, this is about interventional reasoning. This is what would happen if I do X? What would happen if I give this if I give a loan to someone? Would this help their like how they develop in life? Or if I have certain what is the term? Subvention in English. Some German speaker. So, and yeah, if I give certain subsidies to a certain type of industry, what will happen later on? This is just something, you don't have data for this, but there is no interventional data, but you still want to make predictions. What would happen if I give this? And you need to take into account the downstream effects, etc. And again, with structural causal models, we can have a duplicate of the structural causal model, where here we have this interventional variable t, and in one version, we actually have this do operator on there and cut all the incoming edges to the t, because we actually go and do a hard intervention on this t. And then we learn to basically take into account in a real world setting the observational data that I have for this, and then a hypothesized intervention and the X data without the intervention, and then predict the interventional Y data. And this actually also substantially outperforms standard methods for interventional studies. So we can also do conditional average treatment effect evaluations of this, and yeah, have a new state of the art there. So I'm super excited about this. We sort of solve problems where some of the causal community would say, this sort of seems like you shouldn't be able to do this, but we are able to do it because we have a prior over the structural causal model. So everything is sort of with respect to our prior, but then we can actually answer a lot of interesting causal questions. All right, so I'll end here. The takeaways are TabPFN is a new default for small tabular ML, currently up to 10,000 data points and 500 features, but we're scaling it further. some unique features compared to previous non-foundation models. It's faster. It's just a forward path. Foundation model, it's really nice. There's no HPO needed, much more interactive data science because of that. Better peak performance and works well with less data. And it's actually more interpretable, not less interpretable. And fine-tuning clearly improves performance, so you can customize it to all kinds of different use cases, which we shall do in the ELLIOT proposal. All right, I'll end here. Thank you for your attention. We're hiring, shameless plug. We're trying to build a world-class team, best of the best, and still diverse. So we have like over 2,000 applications, but still we want to get the best people. And if we hire your referral, we'll actually thank you with $5,000. Thank you.